Thanks everyone. Thanks for coming by. Thanks for staying until the very end of the conference day. So I'm Thang Lu from Stanford. This is John Work with Hugh Pham and Chris Manning. So continuing from the keynote yesterday, I'm very excited to talk about how we improve the attention mechanism for neural machine translations. So we just give you a one-slide summary of my entire talk. So there are two recent innovations. One is neural machine translations, which came out just last year, but it has given really promising results. So we got state-of-the-art results for English to French translations at ACL just a few months ago. And Jin et al. 2015 also have state-of-the-art results for English to German. And the other thing I want to talk about is the attention mechanism, which proposed by Badanao et al. 2015 for machine translation, which try to learn to both translate and align at the same time. And this is a really nice innovation, not just within machine translation, but also across a wide variety of different deep learning applications, for example, control problems, or speech recognition, or image captioning. So in this work, I propose a new and better attention mechanism, and also I examine other variants of the attention models. So the nice thing we got is we have new state-of-the-art results for the WMT English to German task. So let me just walk you through a little bit about neural machine translations. It basically is just a big RNNs that train end to end. So for example, if you have two sentences, one from English and one from French, so we will have an RNN that goes through each word one at a time. And this RNN can also be a multi-layer RNN as well. So when it reaches the end of the sentence symbol, it switches into a decoder mode where it starts producing translations. So as previous, it also produces one word at a time, and then you fit in the previous word to generate the next word, and you continue until the very end when you get the end of the sentence symbol, and that's the end of, you get the translation out. So why do we want to do neural machine translations? So one thing is it can generalize well to long sequences. You can think of this model as like 50 or 100 gram language models. But the nice thing is you don't have to explicitly store all the possible sequence of words, and there's no phrase table at all. And it's also a very simple left-to-right beam search decoder. So it has many nice properties. And for the attention mechanisms, it's a nice way of having a memory for the model instead of trying to compress everything until the end to get a single vector that captures the entire sentence meaning, which will cause problem if you have very long sentence. So with attention mechanism, the idea is you keep track of the entire short hidden state as a memory pool, and then as you translate, for example, when you translate at the second word here, you're going to pick the target hidden state and try to compare with each of the individual source states. So we compare with the first source state, we got the alignment weight 0.6, we go on 0.2, 0.1, and 0.1. And until the end where we start we compute a context vector, which is just a weighted average of all the short hidden states. And given the context vector, we can combine with the current target hidden state, we can translate. And with this mechanism, we can able to translate very long sentences. However, there has not been any other attention architecture explored for machine translations except for the work by Badanao. So in this work, I propose a new attention mechanism, which I call it local attentions. So the idea, we want to have a focused attentions. We don't want to just look at the entire short hidden state. At this time, we only want to look at a small subset of hidden state. And we actually show that it gets better results. And not just that, we look at, what? It's so fast. Sorry. Okay. And not just that, I'm trying to look at other variants of the model proposed by Badanao. And I call this a global attention because it looks at the entire short hidden states. So if you're familiar with the work by Su et al. 2015, this is known as sub-attention. Okay, so I first start talking about global attention first, and then build up from that, and then talk about local attentions. So it's very similar to what I have been telling you, except that now I'm going to zoom in a little bit. So we talk about how we compute the alignment vectors AT here. So in order to compute the alignment vector, you need a scoring functions which compare between a target hidden state HT and the source hidden state HS. So there are many ways. I leave the details for you to find out in the papers. I just want to point out that we consider different versions of these functions, like dot product, general dot product, or simple feed-forward network. And the last version is the one considered in Now work. So once we got the alignments vector, we can compute the context vector by just taking the weighted average over the source hidden states. And given the context vector, given the target hidden state HT, we can have a small feed-forward network to compute what I call an attentional vector H tilde T. And given that, you can do predictions to generate the next target work YT. So for the local attentions, everything stays the same, except for one part where I try to predict the aligned position PT. And this PT actually defines a focus attention where I only look at the windows PT minus D and PT plus D. So I won't look at the entire source hidden state, but actually look at only these hidden states within this window. So this here, if you're familiar with the work by Su et al. 2015, this is a nice blend between soft and hard attentions, because we don't look at all of the works, or we don't look at a single work, we actually just look at a subset of work. And also, the nice thing about this model is it's differentiable. So unlike the hard attentions, where you have to do things like reinforcement learning or sampling-based techniques. So some of you might wonder, how do we get the aligned position PT? So what we do is we actually try to predict them. So I have a small feed-forward network that tries to generate values between 0 and 1 by means of sigmoid. And from the value of that network, I multiply with the source sentence S, which gives me real values between 0 and S. And this is where we have the aligned positions. But then there's another question comes up. How do we learn the position parameters WP and VP? Because if you look at this entire setup, there's no connection between this feed-forward network, WP, VP, with the rest of the models. So we have this nice trick where we try to plug it into our model. So I explain that through this example here. So let's say you already predict a position PT, which is 5.5, and the window size 2. So that means we're going to look at the window from 3.5 to 7.5. And what we do is we compute the alignment vector just like the global models. So for every integer S within this window, so 4, 5, 6, and 7, we compute the score just like before, and we normalize them to get alignment weights. And now here's come the trick. So we actually look at a truncated Gaussian with center at the aligned positions. And that gives us a way to either to favor points that nearer to the center. So when we take the previous alignment weights, multiply with the truncated Gaussian probabilities, it actually sharpens the distribution. So now you see that there's only one peak, which is the aligned position at 5, which is near the center, as compared to the previous one where we have 2 peaks, 4 and 5. And also because of that connection here, now we can have everything. We can have the backpropagation path going through BT and go down to WP and VB to learn how to predict position as well. So this model is differentiable almost everywhere, and this works in practice. So just one little thing at the end. If you look carefully at how we define our architectures, when we compute all of these attention vectors, they're actually independent of each other. So whatever we make decision at the previous time step, the next time step won't know about that, which is not so good, I think, because like we know in machine translation, people often keep track of a coverage set to maintain, to remember where we have, which work we have translated, which work we have aligned. So we should really want to inform the model about past alignment decision. And then here in this case, we just try to fit the previous attentional vector all the way down to the input of the first layer at the next time step. So I would say that there are various ways that you can accomplish this. So Bernard work already done that in a way. So they try to have the context vector within the attention layer and they connect to the next time step. But there has not been any analysis of whether this connection is important or not. So we analyze this in this work. So for this experiment, we look at English to German translations with 4.5 million sentence pairs. And we train a very big network, 4 layers stacking RSTMs, 1,000 RSTM cells, 1,000 dimension embeddings. So we limit our vocab size to 50,000 words on both sides. So let's look at the English to German WMT14 results. So the Windows system 2014 has scored 20.7, and we start with a very lousy system which only got us 11.3 blue points. So we then start adding non-techniques. So there's a non-technique that if you revert the source center, you can actually learn better. We got 1.3 blue improvements. And if we add dropout, we get another 1.4 improvements. And when we add our global attention model, we get another 2.8 improvements. And with our fitting input approach, we got another 1.3 improvements. So in total, we get around like 9 blue point improvements, which is really nice. However, we haven't got to state the art yet. So let's work more. Oh, by the way, I just want to tell that there's a nice observation that we had last ACL that there's a really nice correlation between perplexity and blue score. As you can see in this table here, with smaller perplexity, we actually get better blue score. So if we put other work, other neural machine translation work in context, for example, the G-Nodal work, so there's an RNN search model there, which is very similar to our attention model. RNN search is the system that have attention. So you can see that our model is on par with the RNN search model. And when we add fit-in input approach, we actually get better performance. So the current state of the art have many different features, like it have a non-word replacement. It have large vocabulary of 500,000 words, and it have an ensemble of like 8 different models. So to beat that, we start having different things. So we have local attentions, which give us 0.9 blue improvements. And we also do the same thing, the unknown word replacement technique, which has been done in the past, very useful. It also indicates that this attention model can learn good alignments for unknown words. So we get another 1.9 blue improvements. And then when we ensemble 8 different models with unknown word replacement, we get 23 blue points. And this is 2.3 points better than the phrase-based system and 1.4 point better than the Montreal system, which is also a neural machine translation system. So moving on, we also try our models on the WMT15 English to German experiments. So again, the model can generate really well. So we get a new state of the art as well, 25.9 blue points. And this is 1 blue point better than the Montreal system, that has won the competition just this year. And that system had both the neural machine translation components as well as the 5-gram language model re-ranker as well. So I think this is really encouraging. And when we test our system on the other direction, from German into English, we got similar again with attention and fitting input. Okay, so for some analysis, I'll look at the learning curves, how we translate long sentences, the alignment quality, and the sample translations. So as you can see here, these are the learning curve for different systems. We have the x-axis, the number of training media batches, and the y-axis is the test cost. So the top 3 curves are the one without attentions, And it's really nice to see that with attention, we clearly have better learning curves with lower test cost. And as we motivate at the beginning, that attention model can translate long sentences really well. So we did something similar to Butter Network, where we group sentences by length, short sentence first and then long sentence later. So the red curve here is the model without attentions, and you can see that it translates poorly as it goes to work longer sentences. And with all of these models up here, these are attention-based model would translate really well for long sentences. And for our best system, which is the blue plus curve, it's actually better than all other system over all categories. Okay, so for the alignment quality, in the past, people evaluate these attention model by only looking at whether the models perform well for unknown word replacement or whether you can visualize it nicely, but they haven't evaluated overall through the Go data set. So in this work, we look at a set of 500 sentence pairs with Go alignment, and we force decode our model so we can get the alignments out of it. So we can see that as we have better and better models, the alignment error rate keeps going down. And with our best model, we get like 0.34 alignment error rate, which is competitive compared to the Berkeley aligners. So let's look at some sample translations. So here the source translations, the human translations, our best system translations, and the base system which doesn't have attentions. So as you can see that the model can actually translate names really well, whereas the one without attention, it sort of knows that it needs to put some name, but it doesn't have the strong connection with the source side to pick the right name to translate. And also we noticed there's one interesting case where we have the doubly negated phrase, not incompatible. And our model, the best model, actually got the doubly negated phrase correctly. So whereas the other model, it missed the which actually get the reverse meaning. If you're wondering what is the human translation of this phrase, it's actually a very fancy one with 6 different words in blue up there. And we also noticed that the models also fail sometimes, like when it translates this phrase, passenger experience, it missed that phrase entirely in the translation. So lastly, I'm glad I'm translating into English as well so that I can understand some of the translations. So if I look at the translation of the best system, it actually gets the meaning exactly correct. It has some paraphrasing, for example, like the reference had the phrase couple with the straight jacket, and the best system have the phrase in connection with the straight jacket, which I think has similar meaning. Whereas the base system, it messes up the structure. So that indicates that this model can also translate well long sentences. So in summary, I propose 2 effective attentional mechanisms, global and local attentions, where the local attentions perform better. I also saw state-of-the-art result in the WMT English to German test. And we have different analysis to demonstrate that the attention model is effective in various aspects. And also, the code will be available soon in MATLAB. Thank you.
I got the mic first. Very nice talk, thank you. I have 2 simple questions. The first one is, you said that is almost like most of the thing differentiable. So what is not differentiable?
Oh, the part that's not differentiable is when the line position, it moves across the boundary, like when it moves like 3.9 to 4.1. And at that time, you have different words. Different source words come into the window. So only at this point, the models become not differentiable.
Right. Thanks. The second question is your biggest improvement come from when you combine edge model together. Could you explain a bit about that? Which edge model you combining and why it improved a lot?
Oh, I see. So this is non-technical. So past work already tried to do ensemble of different models because like it just become more robust. But I think the nice thing here by trying various variant of the attention model, we actually have various models that have very different attribute, and then these contribute together to get a better system. So to be concrete, I ensemble like global attention model, local attention model with dropout, without dropout, and then all together we can get a very nice system.
Right. So what if you just try several variants of that global attentional model and then drop completely the local version? So how about that change the performance? Because like for the local version here, you just gain something like 0.8%, right? What 0.9. So what if you just drop the local one and use the variance?
Oh, so by the way, so only the last slide are 8 model. The rest of the system are only a single model. So we actually compare different architecture fairly. And I also have more results in the paper about different architecture with different scoring function as well. Does that answer your questions?
I'll probably should look at your paper then.
Okay, yeah.
Hi, Rikas Enric, University of Edinburgh. Thanks for a nice talk. So my question is concerned with your comparison to the Montreal system. So your story was all about attention.
That's right.
And you report now 1 bullet point improvement for English-German. I think your German-English system is 3 bullet points worse than the Montreal system. But your systems are different in various small ways. Like you have a deeper network, you have dropout, whereas they don't. And I would really like to hear if you have done any contrastive experiments where you try to find out which differences actually matter for the performance, because you've now been glossing over that.
Yeah, so I would say that in deep learning it's really hard to compare different models. But I mean, if you can go to state of the art, I think that is something concrete that we can go towards. And in terms of comparing different things, I think we try our best. So I think first of all, I just try to compare relatively among the different versions that I have. They all have the same 4 layers network, the same dimensions, with like different things like global attention, local attentions. Of course, I would say that we have deeper network, which might be better than Montreal system, but at the same time, Montreal system have things like max out network, deep output. So it's really hard to do an apple-to-apple comparison here. And just to point out that for the German to English system, we didn't go all the way to train various system. We only have up to the global attention. We didn't have all the different local attention and to combine them. But I think if we push hard, we probably could also be on par with Montreal system as well.
Okay, thanks.
Yeah.
Oh, can I ask a question?
Yeah.
So thanks for a very interesting talk. My question is about the comparison between global attention and local attention at the model level. So as I understand it, in the global attention, you're considering all words globally, but the attention model is still trying to predict a local part of the sentence to pay attention to.
That's right, exactly.
So then for your local attention model, you're still predicting to pay attention to some local part.
That's right.
In terms of model architecture, actually, what is the difference besides the extra local constraint?
Oh, I see. Yeah, so basically, for the global attention, you only have a fixed attention over the entire source sentence. For the local attention, you have the window that can adjust depending where you are on the target side. So imagine that in the future, if you were to translate a long document, which it might be really hard to focus on the entire document. So then you might want to have a little window to move across. Maybe, like, for example, when you translate some word at the beginning, you might want to just look at the attention somewhere at the beginning. And then if you go to work toward the end, you want to just look at the attention toward the end of the sentence, of the source sentence. So I think that is the basic motivation for this work.
I see. So it's not just a computational gain for a local attention model. You think actually in terms of model, it does something better as well?
So I think like for source, like at sentence level translation, I don't see a real computational gain.
Oh, I see.
But I would expect that if you were to translate document at paragraph level, you will see a clear computational gain.
Okay, thanks.
The model.
Okay, really nice talk. It's very interesting you do some evaluation on the word alignment generated by the attention and generated by the conventional methods. Have you? I'm wondering if you have conduct any human analysis on these word alignments. Are there any differences?
No, we only look at the alignment ourselves. So we plot some of them, but I think we didn't do any human evaluation on alignments or on translations. I think it would be really nice if we can have some error analysis on these kind of neural machine translation system to find out, where do these models make mistakes.
Any final questions? If not, let's thank the speaker and close the session. Thank you all.
Thank you.